Assalamualaikum and good day. I bid to everyone. Today we're going to learn the very last subtopic in our organometallic course, which is on uses of some organometallic compounds. We are going to be focusing on their catalytic properties or activities. So there will be four examples that will be discussed under this subtopic. But for this video, I'm going to discuss on the first two examples only. So the last two will be discussed later in the next video, and probably that will be our very last video. And inshallah, we are going to finish all the syllabus right after Raya. There'll be one or two more examples to be learned. Now, in order to be able to be a good catalyst, your organic compounds must be able to undergo two processes: reductive elimination and oxidative addition. We have learned these two chemical reactions before this in the previous video, and I do hope you still remember what are they, how they are going to be like, what are the changes that might be involved before and after the reaction, and so on and so forth. So that's the first thing that you have to understand, the chemical reactions behind the catalytic activities of your organometallic compounds. And the second one would be the effective atomic number. How many numbers of electrons are there in any given metal in your metal complex? So these two things are the most fundamental parts that you have to understand in order to comprehend the lecture that I'm going to give you in a few seconds. So bear in mind that oxidative addition and reductive elimination processes are happening in a cyclic manner. So meaning you might be seeing reductive elimination first and oxidative addition in the latter process, but they are actually happening in the full cycle, because catalyst, if you still remember, the definition of catalyst is any material, any substance, any chemical substance that is able to speed up the rate of reaction without it itself being consumed in the reaction. So if you want to use the catalyst, you must make sure upon completion of the process, your catalyst will be back into its original form. That's why it must be in the cyclic manner. Now look at this first example. So example number 1, we have eta 5. This is cyclopentadienyl. We have tantalum and trihydrite. So the whole process or the whole reaction is called deuteration. So I want you to find out later what is deuterium. Deuterium. Sorry, it is wrongly spelled. So the whole process is actually deuteration. So we are adding deuterium into the whole benzene. So from benzene with 6 hydrogen, we want to replace all the hydrogen with the deuterium. Okay, so we have tantalum here. So that's why, remember I said just now, you have to know how to find the EAN, effective atomic number. For tantalum, why do you have 18 electrons? So cyclopentadienyl will contribute how many electrons? Hydrogen, how many electrons? Hydrogen is the easiest one. That's going to give you 1 electron each. Okay, so you must know how to total up the EA, the EAN. Okay, and then this is 18 electrons. Now 2 hydrogens removed. This is the first step. So you are going to get this structure: only 1 hydrogen left and 2 cyclopentadienyl. So definitely, since you are removing 2 hydrogens, the total number of electrons now has become 16 electrons. Now next, you add benzene. Okay, now benzene is now attached to your tantalum complex. So in this case, it will give you 18 electrons back, because 1 benzene will give you 2 electrons. Okay, so from here you should know two electrons and then two electrons, tantalum from which group, and cyclopentadiene from which group. So definitely you can tell um, where are they from. You can tell the number of electrons. So it's gonna be giving you 18 electrons back. So next, you are going to remove two hydrogens. You're going to get 16 electrons. So now there is no hydrogen left on the tantalum. And step number 4, when there is no hydrogen left, only then you can add your deuterium. You add 2 deuterium, there will be 2 deuterium here, making 18 electrons for the EA end for tantalum. Last but not least, you have to remove your benzene now with the newly added deuterium and leaving your tantalum with 1 deuterium and then 2 cyclopentadiene. This complex will undergo the whole process again from second step until the fifth step, until you get all hydrogens replaced with deuterium. So described below is the mechanism. The first one is loss of hydrogen. So this is reductive elimination. Why it is reductive elimination? Because 18 electrons now reduced to 16 electrons. I'm not going to go in details how to calculate the EAN. I hope you do know how it is counted. Okay, based on number of electrons contributed by each ligand as well as the location of your metal in the periodic table. The second one would be the complex. This is your catalyst reacts with benzene molecule, and this is called oxidative addition. Why it is called oxidative addition? Because from 16 electron now it has become 18 electrons. So there is change. There is an increase in oxidation numbers. So that's why we name it as oxidative addition. And bear in mind the bond between benzene and the metal is called sigma bond. The third step would be removal of hydrogen. So this is also reductive elimination because from 18 electrons now it has been reduced to 16 electrons. Okay, there is a reduction in oxidation number. Now from this to step 4, the complex adds 2 deuterium. This is oxidative addition because from 16 it is becoming 18 electrons to form this species. We have Cp2, tantalum, and D2. And the last but not least, the fifth step would be the complex eliminates your benzene C6H5 with one newly added deuterium. This catalyst will undergo the same process from second step until the fifth step until the whole hydrogen is replaced by the deuterium. Okay, so as I said earlier, this is happening in the cyclic manner, so you have to make sure that at the end of the reaction, you will get back your catalytic species in their original form. We are clear with that on the first example. The second example will be on the Monsanto acetic acid process. If you still remember, we have learned about carbonylation and the insertion reaction. So this is it. So overall reaction, we have carbonyl, we have hydrogen. This reaction is catalyzed by copper and zinc, producing methanol. So we don't want methanol, we want methanoic acid. We want acetic acid. Sorry, you want acetic acid or ethanoic acid. So further reaction will be your methanol converted into your acetic acid with the assistance of carbonyl, rhodium, as well as iodide. Okay, so when this is used, we can get the acetic acid. So how does it work? Now look at the mechanism. The first one, iodide converts methanol into methyl iodide. So from methanol to methyl iodide, because methanol reacting with iodide to form methyl iodide. And then you will produce also water. Okay, and then rhodium reacts with carbonyl and also iodide to produce the catalyst. So rhodium with 2 carbonyl and then 2 iodide. The catalyst undergoes oxidative addition with metal iodide. Okay, meaning your catalyst, you react with the metal iodide. The whole process is called oxidative addition because there is a change in oxidation number. We are going to look at this in detail slightly later. And then producing this complex. Then number 4, insertion of carbonyl into the RH metal. So between metal and metal, there will be an insertion of carbonyl. If you still remember, we have learned this, that carbonyl will be inserted between metal and methyl. And then number 5, the complex will undergo reductive elimination, eliminating your what we call this acetyl iodide and regenerating the catalyst. So the acetyl iodide will react with water because initially we produce water. In step one to form your acetic acid or ethanoic acid and hydrogen iodide. So 3 to 5 will be repeated in a cyclic manner to supply methyl iodide with a byproduct of water. So you need water, you also need methyl iodide. Now let's see again the step. Step 1, we have methanol. Methanol converted into methyl iodide. We need this methyl iodide in oxidative addition. We also need this H2O later to produce your ethanoic acid. And step 6, you see here, this is acetyl iodide reacting with water, producing your ethanoic acid and hydrogen iodide. So this is the whole mechanism on how Monsanto acetic acid process is going to take place. So methanol producing acetyl iodide, producing the byproduct, which is your water. And this is your catalyst with 2 iodide and 2 carbonyl. So we have 16 electrons. Again, I hope you still remember how to calculate the effective atomic number for the rhodium here. How many electrons contributed by carbonyl? How many electrons contributed by iodide? So you have to know that. Only then you can count the EN number correctly. And now you add this iodide, acetyl iodide, into the structure. Now we have 3 iodide here, 1 methyl, and 2 carbonyl. You insert carbonyl. Where to insert this carbonyl? Between methyl and metal. So you're going to get carbonyl here with 18 electrons. So there is no change in oxidation number. So this is just an insertion reaction. 18, 18. But there is an increase in oxidation number from here to here. So we call it oxidative addition. Now from this complex, we are going to undergo reductive elimination. You are going to remove acetyl iodide. Remove acetyl iodide, meaning CH3, C-double-O, and 1 iodine. So you're going to get acetyl iodide, and you're going to get back your catalyst. This is called catalyst regeneration. You regenerate the same catalyst again, because these catalysts will undergo the same process again to produce your acetic acid. Now what happened to this acetyl iodide? Acetyl iodide will take water, react with water to produce acetic acid. So that is the whole process. Easy, right? So we have learned 2 things here. There are 2 examples that I've shown you here. Let us revise. The first one is on the deuteration reaction of benzene. All hydrogen in the benzene replaced with the deuterium. We are using cyclopentadienyl tantalum trihydride as our catalyst. So we see that reductive elimination as well as oxidative addition are taking place here. Okay. We also learned about Monsanto acetic acid process, where we use rhodium with 2 carbonyl and 2 iodide here. So we use carbonyl and hydrogen gas to produce methanol. This methanol will be further treated and reacted with carbonyl and also iodide to form acetic acid. So we need to see the details of this mechanism from methanol to acetic acid. How is it going to be like? The first thing first is your methanol converted into methyl iodide and water, and then in the last step, your methyl iodide will react with water to form acetic acid and hydrogen iodide. So this is the whole mechanism of your Monsanto acetic acid process. So before I end, I would like to remind you again that you have to go back to the previous lectures and please find out how to find the electron atomic number for your metal, because we're not going to go details here. We have learned that before. And if you have that in mind, if you have understood everything about EAN, and also you have mastered the knowledge about chemical reactions, especially reductive elimination and oxidative addition, then you don't have any problems in understanding this lecture. Thank you very much for your kind attention. See you in the next video.